Mean free path. So the molecules in the gas travel in straight lines until they run into something. They run into the sides of the container or with other molecules. And what we mean by mean free path is the average distance that they travel between collisions. It's an average. That mean means average. So some will travel shorter distances, some longer, but the average distance that they travel. As an example, if nitrogen was the size of a golf ball, remember we said if nitrogen was the size, maybe it was argon, if a gas molecule is the size of a golf ball, its nearest neighbor is going to be about 40 feet away. If nitrogen is the size of a golf ball, it would travel about 40 feet before it ran into something. So that kind of gives you an idea for the sorts of collisions these things are having. This mean free path is going to decrease as the pressure increases. So if we look at this gas, if we squeeze those particles closer together, I think it only makes sense. They're crowded now. They're not going to be able to travel as far in a straight line before they run into something else. So that mean free path goes down. Here are two processes that you need to know about. Diffusion, or diffusion I should say, and effusion. So very similar words, and they both have to do with gas molecules spreading, but there's an important difference. So diffusion is gases spreading from a high concentration to a low concentration. And so like if I were to spill something smelly up here on the front desk, and there was no air currents or wind blowing in the classroom, eventually the odor of that would pervade the whole classroom, right? And the odor is helpful because we can detect it. We can't see the gas particles moving around, but we can smell when the particles come to us. So if the particles are heavier particles are going to move slower. They're going to diffuse slower. It's going to take them longer to get across the room. Effusion is the process of a gas escaping through a small hole into a vacuum. So you've got a container, and it's surrounded by a vacuum, and there's this little tiny hole. And the gas is getting through that hole into the vacuum is what's called effusion. The rates of diffusion and effusion are both related to that RMS average velocity, root mean square average velocity. And what that means is at the same temperature, the rate of gas movement is inversely proportional to the square root of its molar mass. Because our equation there was root mean square velocity was 3 RT over the molar mass. So larger molar mass, lower root mean square velocity. Graham's law of effusion describes the rates at which gases effuse. So here is an effusion apparatus where we've got a gas over here and, oops, nothing. We have a vacuum over here. There's a hole, and these particles are going to escape through the hole into the vacuum. Smaller particles are going to escape faster than larger particles. And a balloon is not technically experiencing effusion because it's not going into a vacuum. But a helium balloon contains helium but other gases as well. The helium escapes first, though, because it's the smaller gas and it moves faster. So it's related to molar mass, but the reason it's related to molar mass is because the velocity is related to the molar mass. So this equation is important. We have the rate at which A effuses divided by the rate at which gas B effuses, and that is equal to the square root of the ratio of their molar masses. But notice this is upside down. Here A is on the top, and here A is on the bottom. because the larger a molecule is, the slower it effuses. So if it takes 1.25 minutes for 0.010 moles of helium to effuse, how long will it take for the same amount of ethane to effuse? Well, the rate of A divided by the rate of B is equal to the square root of the molar mass of B divided by the molar mass of A. What is a rate? Bless you.
Something over time?
It's something over time. Like a rate of speed is distance traveled per unit time, right? So did they actually give us the rate at which helium diffuses? No, they said this many minutes for this amount. So we could say that the rate for helium is equal to 0.010 moles per 1.25 minutes. And that would be the rate. That looks like a strange H. So we're looking for time. How long will it take for the same amount? So if we found the rate for ethane, we could find the time because we know this amount, this number of moles. This is the ratio of molar masses. Do we know the molar masses? We can figure them out, right? So I'm going to change these from A and B. We want to find the rate for the ethane. So I'm going to put the rate for the ethane on top just to make life easier, and the rate for the helium on the bottom. Then this is the molar mass of helium, and this is the molar mass of the ethane. So that tells me then that the rate for ethane is equal to the rate for helium times the square root of the molar mass of helium over the molar mass of ethane. I took this equation right here. I multiplied both sides by rate of HE. We canceled that on this side, and I moved it to that side. So here we have our rate of HE. Let's go ahead and calculate that. 0.01 divided by 1.25. 0.008. 0.008. Should have two sig figs. Moles per minute. So that's the first part, 0.0080 moles per minute. And then what is the molar mass of helium? 4.002. Now this is the ratio of their masses. So if we do it in grams or if we do it in kilograms, it doesn't matter because it's going to cancel out. So grams per mole. How about ethane? Well, we've got 2 carbons times the mass of carbon, plus 6 hydrogens times the mass of hydrogen. So 30.068. grams per mole. So these units cancel out. So we've got 4.002 divided by 30.068. And we press equals on the calculator and then press the square root button and then multiply by 0.008. So the rate for ethane is going to be equal to 0.002919 moles per minute. Did I do it right? We're looking for time for 0.01 moles. So if I take 0.010 moles and use that rate as my conversion factor, that will give me time. So I'm getting 3.4 minutes. Oh, I completely ran out of room down there. Yes?
Do you need to convert the grams into kilograms?
That's a good question. Do I need to convert the grams into kilograms? Because this capital M was in kilograms per mole. Because it's a ratio, if I convert it to kilograms per mole for each of them, I'd still get the same answer, but it's not necessary because they cancel out.
If we only had one,
If you only had one, you would have to take that into consideration. And you can get problems where they give you both of the rates. They give you one of the molar masses and they give you the other. And so these are going to have the same units, grams per mole or kilograms per mole. So this is the maybe more sophisticated way of not converting those. If you feel like that's going to mess you up, go ahead and convert them. That's fine. It's an extra step. My head hurts, feeling lazy. Only two. Why only two significant figures? Because this number, 0.010, only two sig figs. So that ended up limiting the whole thing. Good question. This is also not a big deal. Stoichiometry, big deal. Nomenclature, big deal. Balancing reactions, writing reactions, big deal. Gas laws, big deal. This, little deal. Okay?